Thank you, Dr. Monis Jacob. Thank you, sir. Am I audible? Yeah, is it on? Am I audible? Hello, sir.
Yes.
Okay. Thank you. So, thank you for the introduction. Let me just start sharing the screen. Whether the PDF file is visible to all? Is it got shared?
It is visible. You may make it a presentation. It is not.
Okay. Now it's fine? Okay.
It's fine.
Okay. Thank you, Teja. So, today's talk is beauty of linear algebra. So, here basically what I have done, my target is actually not with a lot of proofs and all this. I have just tried to give some applications and made it in such a way that there will arise some intuitive questions and the answer will automatically come also, because I have given lots of examples also. So from that you can generalize the results, okay, and the applications also, and some of them I have taken from even the Wikipedia and many books. I'll show all those before that. Okay, so these are some of the special matrices. When we were introduced about matrices, we didn't get actually during that time what is the beauty of those matrices. I will say these are some building blocks of all those matrices. So to show that, I need some decomposition, and I will deal first with those decompositions. The decompositions or factorizations of matrices, right? So you must be knowing about this fundamental theorem of arithmetic, which gives, suppose you are given with any number, natural number, then you can always factor it into some prime factors, okay, and that is also unity. So there are two concepts. One is that uniqueness is there, and another one is you are getting smaller prime numbers. Okay, with the help of that, you can always determine the GCD and LCM of two numbers. So there, if you can factor to bigger numbers, you can always say means what is the common factor or not, whether there exists a common factor between these two numbers or not. So basically, this prime factorizations gives actually these are some basic building blocks of all numbers, right? So matrices, and if they are complex, then the counterpart, that's your unitary matrices, right? And so this way it looks like A can be, if it is a rectangular matrix of order m cross n, then you can get a matrix U of order m cross n and a matrix of order V of order n cross n. And these two are unitary matrices. That means U conjugate transpose is equal to identity, and this is of order m, and V conjugate transpose, that's your identity of order n. And what is your sigma? Sigma is a matrix. You can consider it as a diagonal matrix, but it may not be always rectangular. Like here, it is m cross n. So basically, these entries, the diagonal entries here, then some rows or columns will be 0 here. So basically, here is one row which is completely 0. So these are some diagonal entries, and these diagonal entries are called here singular values of the matrix. And what more information it gives? Immediately, the number of non-zero singular values of a matrix A is nothing but the rank of the matrix. So if you can represent a matrix in singular value decomposition form, from that you can immediately say what is the rank of the matrix. Okay? And this U and V, the columns of U and V are called the left singular vector and right singular vectors of A. Right? And this is the intuitive interpretation of SVD, or the singular value decomposition. Here, this is actually unit disk, and these are the canonical basis vectors. These are the two canonical basis vectors, one in magenta color and another in yellow color. So what happens if you compose this B star? That means B star forms, then sigma, then U. This composition, what it gives, like B star, if we compose, actually it is rotating this basis vectors. Next, if you use the sigma, then it gets scaled up. And the sigma 1 and sigma 2 here represents basically the semi-major axis and the semi-minor axis. And if you choose again an unitary matrix U, then it again gets rotated. Right? This is the implementation of matrix A, and this is the visualization of U sigma V star. So basically the singular values can be interpreted as the magnitude of the semi-axis of an ellipse in 2D. Right? This is the relationship between SVD and eigenvalue decomposition. So all we can say, we know singular values and we know also eigenvalue of a matrix, then how they are dependent or how they are related. So suppose A is a matrix which has this singular value decomposition U sigma V star. Then if we compute A star, this is Hermitian. Similarly, A star A is Hermitian also. If we are computing A star, that's coming out U sigma V star, V sigma star, U star. Simplification it gives, because V star V, that's your identity. So it gives us your U star. Similarly, A star A, it gives V star, sigma V star. So what are the consequences here? So the first one, the columns of V or the right singular vectors are the eigenvectors of A star A. How we are getting it? Basically, this is suppose the matrix B, we can say A star. Suppose this is B, then B into U is coming out equal to U times some matrix, a diagonal matrix, right? So what we got again from your eigenvalue decomposition, you can always say these columns of V or the right singular vectors are the eigenvectors of A star A, and similarly the columns of U or the left singular vectors are the eigenvectors of A star. And how these non-zero eigenvalues are related? Suppose we are dealing with the non-zero singular values of sigma, then they are the square root of the non-zero eigenvalues of A star A and A star. Definitely it gets squared of it. So they are related by the square root of the non-zero eigenvalues of A star A or A star. Right? Here is one example. We have one matrix of order 3 of 2, and this is a full column rank matrix. So it's of rank 2, And if we compute A transpose A, I'm considering A transpose here instead of A conjugate transpose because we are dealing with a real case. So it will be same as A transpose. A transpose A is 5, 2, 2, 8. This 2 cross 2 matrix, and A transpose is a 3 cross 3 matrix we are getting. And in both these cases, the eigenvalues are coming out 9, 4, and here the eigenvalues are 9, 4, 0, and we know this result term. So if A and B are, means we can A is of order m cross n, B is of order n cross m, then AB we can have as well as BA we can have. Then we know a result that AB and BA have the same set of non-zero eigenvalues, and you can see here also the same result. 9, 4 is the non-zero eigenvalues which is appearing in both the cases. Then the eigenvectors are 1, 2 here, and the corresponding eigenvector for 4 is 2, minus 1, and similarly these are the eigenvectors corresponding to 9, 4, 0. Then A can be expressed as U sigma V star, and here what is my U? U is okay. So these vectors I am combining it in a matrix, and I am normalizing that means I'm taking actually its modulus and dividing it, then again its modulus, so normalizing it. Then what happened next is this matrix 3, 2, it is coming, its square root actually, right? Square root of 9, that is coming 3, and square root of 4, that's 2, and next one is again these two columns, right? Now, applications of FBD. It has lots of application. I'll talk about this in while solving homogeneous linear equations. Also, this has application. Another interesting is about finding pseudo inverse. What is that? Basically, we know if a matrix is non-singular, that means if all its eigenvalues are non-zero, then it has an inverse, and it has to be a square matrix also. So whether we can generalize it to a matrix which has 0 eigenvalues, whether we can generalize it to a matrix which is not square, so there comes the idea of pseudo inverse. So if A is U sigma V star, then A pseudo inverse is V sigma star U star. No, star, this is actually sigma dagger. Actually, what is the sigma dagger? It's again a diagonal matrix, may not be square, and the non-zero entries will be actually the reciprocal of its non-zero entries. Okay. Then this SBD and pseudo inverse have application in signal processing, image processing, and big data, and all this. Let's see some of the examples. Okay. Before dealing with this, let's talk about images and pixels. What are pixels? Pixels are basically the smallest unit of picture. Suppose this is one picture, so these smallest squares add some pixels. Okay. So, next, what is then a picture or a digital picture? It's basically a function again. That's from R2 to C, where C is a color space, and what it consists of? It consists of 3 components. It's again a subset of R3, and if we are dealing with 256-bit color type or something, then it will range from 0 to 255 and all this. And each component, that means a color component or a color element, it has 3 components, right? Because it's an element of R3, and each component will take a value from 0 to 255, and the first one will stand for red component, second one is for green component, next one is for the blue component. Basically, this is the RGB format. You must have heard this word, the RGB color component. Means actually 1 pixel is glowing how much amount of the red color, how much amount of green color, and how much amount of blue color. With that a color is coming. Okay, and this is how it has been. Generally it has been dealt with. Let's talk about SBD data compression. I have taken this image and all this from this link. You can see actually it has been elaborately described here by and okay. So what is it? Basically, this is an image of a tiger, and it has suppose 500 cross 800 pixels, right? So there are 500 cross 800 pixels, and this is a color image. Let's, for simplicity, consider it in black and white form or in the grayscale format. So we'll consider the tiger in this form first. Okay, so each pixel is the color intensity only, not intensity of the light. So again, it can be of any value from 0 to 255 or any value, right? So basically, this is a matrix of order 500 cross 800 pixel, or 500 cross 800. So it's a rectangular matrix. Now what we are trying, we know this is a full rank tiger, or that means the matrix is full rank type, as rank is suppose 500. And we want to compress it. What we are trying to do here, we want to drop some of the singular values. That means we want to first represent this matrix, which is of order 500 cross 800. We want to represent, or we want to decompose it into singular value decomposition format. So we'll have some U, then sigma, and V star matrix, right? So we have the sigma matrix, and in sigma, suppose the diagonal entries are in non-decreasing order, okay, or non-increasing order. So what we'll do, we'll drop those zero singular values. Those are of no effect here, and those also we can go on dropping also some smaller smaller singular values which are of no importance. At the same time, we are also deleting the corresponding columns from U as well as from V, right? So in that case, we can suppose we are dealing with rank 200 tiger. What does it mean? So we have considered only those first 200 singular values, and rest one we have just didn't consider. We just avoided them. And the corresponding column vectors also we have considered in U as well as in V, right? In that space, it becomes a smaller one, and it takes less space also. I mean, the data in this case gets compressed. And what else? You will see actually the other singular values of not importance. After this 200 rank also, we are getting the same image almost, right? And you can also think of how much percentage it got compressed. So that can be found out like suppose you have the singular values, n singular values, then you sum the total one, means total sum of the singular values, then how much you have just considered. So the one you have considered, that sum divided by the total one, and that percentage, if you consider, that's actually the percentage it got is the new value, and the rest one, that means 100 minus that one, is the compressed value, right? So you can see, even if we deal with the rank 50 tiger, we can find this matrix. So what does it imply basically? It implies, suppose we have a 500 cross 800 pixel image, then we are having this 50 cross 500 matrix for U, and 50 singular values, and 800 cross 50 matrix for V. So basically we reduce the size to a large value. So this is what is called data compression. Next, another application is linear least square fitting problem. What is this? So you see, these are supposed to be data points, and these are distributed, and it looks like they are linearly distributed. Okay, so we want to fit a linear or line which will approximate all these data points. So these data points are basically suppose xi, yi for 1 to n, suppose. Then what we are trying? We are trying to find out a linear equation. Suppose a xi plus b yi minus c equal to 0. So this should satisfy this equation. Ultimately, that means for all I also. So if we represent them in vector form, how it will look like? it will come out to be like this. So A times x1, x2, xn plus B times this and C times minus of 1, now this has to be equal to the 0 vector. In the matrix form, this comes out. You have the n cross 3 matrix. The number of columns is here 3. Number of rows is basically much more here. So it is n here. And AB, so this is the actually unknown we want to find out. And we want to equate it to 0. Right? Then how to solve it? So this is, suppose we got its singular value decomposition as u sigma v star. And if one of the elements is 0, say, the singular value is 0, and then we have the solution. In fact, the solution corresponding to the column of V, that column, okay? That means the singular value, if it is 0, the corresponding column of V is the solution. If there does not exist any 0 singular value, then what we have to do? We have to consider the smallest singular value, and that will be the best approximation here in the linear sense, linear least square fitting problem. So this is a linear least square approximation, and here is that line you are getting, right? Next, let's just talk about this QU decomposition. Sometimes it is called also QR decomposition, but I write it QU, Q for this orthogonal thing, orthogonal matrix, and U for the upper triangular matrix. And here, suppose M cross A is an M cross N matrix, which has n linearly independent columns. Then what happens? We can always factor it into the form A equal to QU, and Q is some M cross N matrix with orthonormal columns, whose columns are orthonormal, and U is an n cross n upper triangular matrix with non-zero diagonal elements. This is important. It has non-zero diagonal elements. And Q may not be always square matrix. It is here one m cross n matrix whose columns are orthonormal. In particular, if m equal to n, then definitely Q becomes orthogonal matrix, and if it is having complex entries, then it will become united matrix, right? See, here is one example. We have this matrix A. This is a 4 plus 3 matrix, and Q is here. You see, this is orthonormal columns. That means this dot product of this column with this one, the inner product, this is 0. Similarly, this, it is 0. And what is this? This is your upper triangular matrix. And the diagonal entries are non-zero. So next, how to get this QU decomposition? There are many techniques. I will only discuss about this Gram-Schmidt process, because this Gram-Schmidt process is already, it has been discussed in the previous lectures. There are also some other techniques like household reflections, Gibbons rotation, and all this. So what we are doing here, first, we have, suppose the A, the matrix we are given with, it has n number of columns, right? So A1, A2, An are the columns of A, and they are of length, say, M, because it's a M cross N matrix. So we can form orthonormal matrices by using Gram-Schmidt process, following certain formula and all this, which has been already discussed in the previous lecture about this Gram-Schmidt process. Okay, so you are getting some orthogonal matrix, and that is your cube matrix. And using some trick, what we are doing actually, and we record U actually during this process, such that this QU becomes equals to A. And U is basically this QI with AZ inner product. QI is the columns of this matrix Q, and AZ are the columns of the matrix A. So here is the example, same example, and what we have done, we have computed P1, the first, so A1 is this one, the first column, second one is A2, A3, there are 3 columns. So B1 Yes, first here is something P1, we have VK, we have computer, then we have computed this projections, then we have computed QK. So V1 is A1, V2 is A2 minus the projection of P1, A2, the general or Gram-Smith orthogonal process. So here we got A2 minus of this value, similarly P3 also this value, and suppose U values, this has to be computed from this range, right? So it is Q2 A3. So what is here Q2? Q2 is half 1 by 2, half 1 by 2. Sorry, all these are 1 by 2, 1 by 2. And A3 is how much? A3 is 1357. So it has to be just added and divided by 2. Right? So how much it is coming out? 10 plus 6, 16 by 2. So it's coming out 8. And that is coming here. This is the 2, 3 entry. Right? So this Q2 with the A3. Another application is pseudo inverse again. And what we know about pseudo inverse, you can take this as granted that if A is an M-cross-N matrix which has n linearly independent columns, then A's pseudo inverse is given by A conjugate transpose times A whole inverse into A conjugate transpose, A star, right? So if we can represent A in QU factor form, then A conjugate, this pseudo inverse is coming out equal to U inverse Q star. So if we can express it in QU form, then we can always find A pseudo inverse immediately using this formula. And this is also immediate. We have substituted these results, and it is, because Q star Q is identity and all this we have applied, so we got Q inverse equal to U inverse Q star, that's equal to A dagger. Now about LU decomposition. L for lower triangular matrix, U for upper triangular matrix, and we have, suppose this is as a system of linear equation. So three linear equation. Here is another system of linear equation. This is another system of linear equation. So which system of linear equation is easier to solve? Let's see. If we deal with this one, we have to go with elimination and all this. It will take a lot of computation. But whereas this one, x1 is already known, and if we substitute this x1 value here, x2 is coming out immediately, and x1, x2 value is now known. We can apply it here, and we can get x3 value immediately. That means using a forward substitution, we are getting this x1, x2, x3 value immediately. This is computationally efficient. And similarly, in this case, you go backward. So here x3 is immediate, and using here you can get x2, and x2, x3 value is known, so you are getting x1 immediately. Basically, what do we say here? This can be represented in the matrix form A. So basically, A times x is equal to alpha beta gamma. Similarly, L times x is your alpha beta gamma, and U times x is your alpha beta gamma. We are trying to solve, in which case it is easier. We are observing that in case of L matrix or the lower triangular matrix or upper triangular matrix, it is easier. So if we can express one matrix A in the form of a lower triangular matrix and an upper triangular matrix, then whether it is computationally efficient to solve this x equal to b. Okay, let's see. Suppose x is equal to b and we want to solve, and we know it can be decomposed into L into U. So we can replace it by L into U times x, and we can write it as LUX equal to, suppose UX is your y. So solving x equal to b is same as first solve LY is equal to b. This will be one lower triangular matrix. L is your lower triangular matrix, so you can use the forward substitution, and then this value of y you can apply here and solve ux equal to y, and in this case because U is opertriangular, you have to use this backward substitution, and that will be again immediate. So using that, let's see one example. Here is your A and the same matrix A, and we have this B matrix 2, the vector B as 2 minus 10 0, suppose. Then the same LU works here. L is this matrix times, means A matrix can be decomposed as this, and so if you will substitute now first we will solve Ly equal to B, that means this matrix times y1 y2 y3 is equal to 2 minus 10 0, so definitely y1 is 2, and similarly we can solve this y1 y2 y3, and then this value will substitute in this equation ux equal to y, and we can get this value of x using backward substitution. The next immediate question is which matrices have this LU decomposition and whether decomposition unique or not. Now what else? If LU decomposition of a matrix exists, if this exists, then how to find it out? That's very important. So let's see. We'll use this technique, that row deduction method. So we are trying to make it one opertriangular matrix by using row operations. So first we need to make it 0. So what we'll do, we'll change this row 2 to row 2 minus twice of row 1, and we'll track this these values. Okay, what means we are whatever values we are using to make it 0, that values will keep a record of it. Okay, so here it is 2, and we get this value. Now next what we'll do, we need to make it 0. So we are taking row 3 plus thrice times of row 1, so this will become 0, and this will come out this. Then ultimately, finally, we will get, using this row 3 plus row 2, you are getting your opertriangular matrix U. Now what happens here? This 2, or here minus 2 we have done. Take the inverse, means the opposite one. Here it is 2, and the corresponding entry is coming here in the lower triangular matrix. The diagonal entries are 1, and this value is 2. And similarly, this is 3 here, so it has to be minus 3. Basically, what we are doing, we are just reversing the process. Okay, and the target is, the way we'll do this opertriangular such that, and we'll record this value so that when it will be multiplied, ultimately it will come out the same result, this matrix A. Okay, so what do we have to do? Whatever value is coming here, that value has to be placed here. And here this 3 value, the negative of this value is here, and negative of this value is here. And the diagonal entries will be always 1. So this one, rows. About uniqueness, you know, any square matrix A admits an LUP factorization. Again, this P is some permutation, that's another thing. Okay, we'll not discuss here. If A is invertible, then it admits LU factorization if and only if, this is a necessary and sufficient condition, if and only if all its leading principal minors are non-zero. So by knowing, suppose you are given with a matrix A which is invertible, and by knowing the leading principal minors, you can always tell whether the matrix can be LU factorized or not. Okay? And if A is singular, then LU factorization happens if the first k leading principal minors are non-zero, although the converse is not true. So this part is having this, that's why this LUP comes out. There is something also like LDU decomposition, diagonal matrix has to be compensated that way. Okay. So what about thinking LL star? That means we are thinking of a lower triangular matrix in LU decomposition, a lower triangular matrix times one upper triangular matrix. What if the same lower triangular matrix, its conjugate transpose is nothing but one upper triangular matrix, and that will work, that upper triangular matrix will work for you in the LU decomposition. And is it possible? Then the next question is, when does this decomposition exist? And whether the decomposition is unique or not. These are the things we want to study. And this comes under this Cholesky decomposition. Here is the example. So you have the matrix A, the same matrix I have considered, and here, probably not the same matrix, this is another matrix. Okay, and This is L and L star. This is a lower triangular matrix, and its conjugate transpose is the upper triangular. So compared to LU decomposition, Cholesky decomposition roughly twice as efficient. So computation is also efficient. And what else we know? If it is Hermitian positive definite matrix, in that case we have a unique Cholesky decomposition, and this is coming from eigen decomposition immediately, or this Q factorization also. We can always have this a to the power half, and a to the power half is suppose QU. Okay, the Q factorization, that means Q is your orthogonal matrix or the unit in matrix, and U is your upper triangular matrix. So in that case, A into A half, A is equal to A half in times A half. That's your U star Q star Q star Q into U. So ultimately Q star U, Q is your identity. So it comes out U star U. So by choosing L equal to U star, you are getting A in the form of L star, right? So this is the proof, immediate one. And what else? If we relax this condition of positive definiteness, and you will consider positive semi-definite, that means there are some zero eigenvalues. In that case, what will happen? This uniqueness will not be there. And here is one counter example. You have A as this matrix, which is positive semi-definite. It's symmetric and positive semi-definite. Its eigenvalues are 0 and 1. But L is here, L and L transpose, whatever you will find, is 0, 0, cos theta and sin theta. That means for any theta it will work. So it's not unique, right? This comes rank factorization. Okay. Again, this is for any M cross N matrix. And if it is of rank R, then it can be expressed as C R form. C is for the column and R for the rows. And C is of a matrix of order M cross R. R is the rank of the matrix. And R is of order R cross N. R is again the rank of the matrix A. So this is the pictorial visualization. So here A is of M cross N. So C has to be of order M cross R, and R is of the order R cross N. Right? In this existence result, every finite dimensional matrix has a rank decomposition. So this is again immediate. And what you can do is A is your M cross N matrix whose rank is R, means it has R number of linearly independent columns. That means dimension of the column space of A is your R. So it must have a basis. Suppose the basis of the column space is C1, C2 up to CR. So what you do, you just consider them in some matrix form, that is suppose C, then any AJ, that is the column of matrix A, jth column of matrix A, that can be expressed as some R1J C1 plus R2J C2, because it's a linear combination, because all the columns of A must be linear combination of these basis elements. So these coefficients, if you combine them, that will form us, that will give us the matrix R. Right, and the non-uniqueness can be easily proven also by considering, suppose A is of C1, R1 is a rank factorization. We choose C2 as some C1M, where M is some other invertible matrix which is compatible. R2 is M inverse R1. Then also it will work, because again it will become C2 R2 is nothing but C1M times M inverse R1. So we'll have another decomposition also. It's not unique. That means, okay. So how to find out this the rank factorization? We'll use this low echelon forms, and using that we will try to find out a rank decomposition of a matrix. So this is a matrix, and this is a root reduction form. That's your D matrix. So, and this is your non-pivot column, because this entry is non-zero, so it's a non-pivot column. So what we'll do, how we'll form this column matrix C, that will consist of the linearly independent columns of A. So this has this non-pivot column. So this column here in A is dependent. So we'll drop that one. So C is of this matrix, excluding this column 3 from the, matrix A. And how much will be our R matrix? From this D matrix, the 0 rows will just remove, and so this will be again of rank 3 here. So because it's a means its rank is 3 here, so you are getting this R matrix here. So this is one way to find out CR decomposition of a matrix. So using also singular value decomposition, you can find out you have suppose A as U sigma V star, then you can write as sigma R, that means there will be some 0 rows and 0 columns, and accordingly you can partition U matrix and V matrix, so V1 star, V2 star, and if you multiply it will come out U1 sigma R V1 star. So basically if you consider U1, that will be a full column rank matrix, and about this one, this will be a full row rank matrix. So you can consider this C as U1 and R as this matrix, right? As application, this is important about Moore-Penrose inverse. This is another pseudo inverse, but this is one important matrix inverse in the sense that it works for any matrix. That means inverse or the pseudo inverse of any rectangular matrix, even if it is a singular matrix or rectangular matrix, it will work. Actually, how we are doing it? Let me tell generally what does it mean by matrix inverse. We have also concept of left inverse, right inverse. Okay, let's talk about inverse. We know if it is a square matrix and non-singular, then A into B is equal to identity, as well as B into A is equal to identity. It means B is the inverse of A. Okay, we'll use the same thing here. What we'll do, suppose it's a rectangular matrix of order m cross n. A is a rectangular matrix of order m cross n, and we'll multiply a matrix of order n times m, okay, such that A into B is a matrix of order, suppose n cross m. So in that case, A into B is identity. So in that case, we'll call B as the right inverse. It is on the right side, okay, and it is working for any rectangular matrix. And similarly, you can think of B into A as your identity matrix. B is of order n cross m, A is of order m cross n. So it will be an identity matrix of order n cross n. So in that case, again this becomes an inverse. It will be called a left inverse, and there is Moore-Penrose inverse, which always is unique, because in other cases the pseudo inverses like left inverse, right inverse may not be unique, but here the Moore-Penrose inverse is important in the sense it is unique, and it follows certain conditions. Like it has to be A cross A is to be equal to A. Means one effect is getting nullified, and similarly A plus A plus is equal to A plus, and also the this way, like A plus whole conjugate transpose is A plus, and similarly this one. So if this condition is satisfied, we call it Moore-Penrose inverse of a matrix m cross n of order m cross n. Okay. So if A is CR factorized, that means we can make a rank factorization of A, and that's suppose you have CR. Then Moore-Penrose inverse of A will be given by R plus C plus, and on simplicity that will come out to be R conjugate star, that means R star, R star whole inverse, C star, C inverse, C whole inverse, C star. So this is a unique matrix, and this will be immediately easier to compute. Okay, this is the way how to find out this matrix A plus. Now about polar decomposition. Okay, I will not talk much about it. Let me skip some of the things. It's about again. It looks like the form of a general complex number. It's Z is UR. U is the complex number number of unit norm, R is that absolute value, or you can say e to the power I theta form. So those are the polar form. So what we are doing here in polar decomposition, A can be expressed in the form U into P, where U is your orthogonal matrix, or if you are dealing with complex matrices, then it has to be unitary, and P is a positive semi-definite matrix. P is here a positive semi-definite matrix, right? So if it can be expressed in this form, then we call this as the polar decomposition of the matrix A. And in this case, as property, you can see determinant A is nothing but determinant of U into determinant of E. Suppose E is a complex matrix, then determinant of U is nothing but e to the power I theta. It will come out because yes, because it's of unit, means determinant of a unitary matrix. Okay, so it will come because its modulus will be 1. All its eigenvalues are modulus 1. So e to the power I theta and P is coming out R. Okay, where R is nothing but the modulus of the determinant A. So it resembles this format. That's why it's called polar decomposition. And we have these results also of a square matrix. If you are dealing with a square matrix, then polar decomposition always exists. And if it's invertible, the decomposition is unique, and P is positive definite. So here is some relationship. If SBD, we have SBD imply the polar decomposition. This is immediate because if it has SBD, that means we have some WP star matrix and sigma. WP star are unitary matrices, and sigma is a diagonal matrix. So A is your SBD. Then you can find, you can choose U as WP star and P as V sigma V star. So UP, right? Okay. Okay, UP is here actually this V star V, that is your identity matrix, so that will be done. So you will get W sigma V star. So this will satisfy, and you are getting A in terms of U and P. So positive definite and U unitary. P is definitely here a positive definite matrix because you have a singular values here which are positive. Okay. Okay. About linear transformations. In my previous lecture, actually once before, I have given also, here I'm not giving lot examples from applications of linear transformation. At least I will say these are some of these linear transformations like scaling, rotation, unequal scaling, shear. Shear means it got, you see actually it got a force from the upper side here. Okay, and it got rotation, it got unequal scaling, rotation, and all this. So suppose you think of an image in your Microsoft Paint or something. So then what you will get some make a rotation also there. So those are immediate applications, right? What else? Okay, I will not talk about the eigenvalues and eigenvectors. These are very immediate. Okay, how these are used in recognizing eigenfaces. What are these? In image processing, processed images of faces can be seen as vectors, whose components are the brightness of each pixel. I've already told what is a pixel, so we are taking only the brightness here, and those are the vectors now. So this is a vector, this is another vector. So the dimension of this vector is the number of those pixels. Okay, and the eigenvectors of the covariance matrix associated with a large set of normalized pixels of faces are called the eigenfaces. So these are some of the eigenfaces, and with the help of these eigenfaces, you can get a face. So these are, suppose you can say these are the basis thing. Okay, some kind of basis thing for the eigenface, or suppose you have any picture of a face, then those faces can be expressed as a linear combination of the eigenfaces. Okay, so basically this is an example of principal component analysis, and these are useful also in biometric system, like we have this nowadays, this Aadhaar thing also. We're having our thumb impression. Also in offices also nowadays, this biometric system is also there. It is recognizing our fingers. Also, it can be helpful for finding, also keep tracking the mischievous activities of thieves and all the peoples. So their fingerprints are already taken, and so somewhere, suppose the fingerprint is means observed, they can compare whose it is. So basically, this works in biometric thing, and also in eigenvoices. This is again a similar thing. You are using nowadays this voice recognition, or means speech recognition system. That means you are saying in your Android phone or something like "Okay Google," or in suppose Apple thing, your iPad, iPhone, you are saying the Siri or Alexa, whatever you are saying, then it is recognizing your voice in terms of their eigenvoices. That means initially it takes your voice and it determines some eigenvoices, and whatever you are saying, it will means take a combination of those voices, eigenvoices, and checks whether it is your voice or not, and try to judge it. Okay, like sometimes you're by saying something, your voice recognizing your voice means your voice can be used as a password. Okay, so basically it is using this eigenvoices. Again, another thing is this principal component analysis. These are actually a huge area, and what we are doing here, use for sophisticated underlying the mathematical principle to transfer number of possible correlated variables into a smaller number of variables called principal components. And so you can go through this. Okay, this is not possible actually to cover all these things. I'm just telling, okay, this principal component analysis is a part of all these applications. You can see data fitting problem already I have discussed, and another application is I can say the spectral graph theory. Okay, it has also a lot of application about graphs. You know what are these graphs? These are actually a set of vertices and set of edges. This is one undirected graph. The edges are undirected. So these are actually distinct pairs of vertices. I call these edges. And we have certain matrices like associated to these graphs. So you have graphs where these graphs are used in any kind of network, like internet network, Facebook network, social networks, any network. So, or maybe interconnectivity like railway networks, airplane networks, means airways networks. All these you can consider any network. So those are basically graphs, and we want to study those graphs and their properties. And we have one of the approach to deal with them. That's a spectral graph theory. What is this approach? We associate the graph with the matrix and analyzing the properties of the matrix and its eigenvalues and eigenvector. We try to find out properties, the structural properties, the topological properties of the graph, the structural properties. Okay, so some of the associated matrices, among some of the associated matrices, adjacency matrix and Laplacian matrix are very well known. There are many more matrices like signless Laplacian, normalized Laplacian matrix, and many more. But we'll discuss these two matrices at this time. And I'm also giving very less applications of it. So what is this adjacency matrix? So G is the graph on vertices 1 to n. So adjacency matrix will be a square matrix of order n cross n, whose rows and columns will be indexed by these vertices. And the ijth entry of the adjacency matrix is nothing but the number of edges between this vertex I and j. And the Laplacian matrix is nothing but dz minus aj. Dz is called the degree diagonal matrix. I'm giving one example here. So this is the graph, it's a G. So what we have done, it is on 4 vertices, so this matrix AJ is of order 4 cross 4. and this column is indexed by vertex 1, this one is indexed by vertex 2, this is indexed by 3 and 4. Similarly, the rows are also indexed by vertex numbers. This is by vertex 1 and others. So diagonally it is all 0 because there is no loop here, and between 1 and 2 there is one edge. So this 1 2 entry is 1 here and 2 1 entry is 1 here, because there is an edge between 2 and 1 as well as 1 and 2. But there is no edge in 1 and 4, so 1 4 entry you can see it is 0. Similarly, the 4 1 entry is 0. So the way it has been defined for an undirected graph, it always becomes symmetric. It's a binary matrix. It's symmetric. Symmetric means all its eigenvalues are real, and diagonal entries are 0. So sum of all its eigenvalues is 0 also. And what about this Laplacian matrix? It is also it is defined as dg minus at. dg is your degree diagonal matrix. You observe the off-diagonal entries are nothing but the minus of these entries in the adjacency matrix, right? And the diagonal entries are the degree of the corresponding matrices. The degree means the number of edges here incident at vertex 1. So degree is here 2, and this degree is 2. So 2, 2, and here the incidence means the number of the degree of vertex 3 is 3. So it's 3 here. And similarly, vertex 4 is 1. So it's 1. So basically, what we are trying to do in spectral geometry, we are given with a graph, we can associate it with a matrix, maybe adjacency or Laplacian matrix or any other matrix. What we are trying to do, we are trying to interrelate or find relationship between eigenvalues, eigenvectors of the associated matrix of the graph to the structural properties of the graph. Okay, the graph structure. So let's give some example. Here, some applications. One important application here for adjacency matrix is, so suppose A is one adjacency matrix of a graph G. Suppose this is a matrix, A is its adjacency matrix. Then A to the power K, the kth power A, and the corresponding ijth entry. This means the ijth entry of A to the power K matrix, okay, is nothing but the number of walks of length K at vertex I, starting at vertex I and ending at vertex J. So that means we need to find out, suppose how many paths are there. It's a small graph, but it may be a huge one. That means it may consist of thousands of vertices and interconnections, maybe much more. But then you don't have to go and search how many are there. That will be much difficult. But what you have to do to find out the number of walks of length K from vertex I to J, you have to find out A to the power K and the corresponding entry. That means A square, suppose it will form, or A cube, suppose, let's consider maybe A square, okay. So this entry is 3. What does it mean? What does it imply? This is actually the number of walks of length 2, because A square we are considering, number of walks of length 2 from vertex 3 to vertex 3. Okay, so that could be if you go from 3 to 2, then again you come back, that's one walk. Again you go from 3 to 1 and again come back, that's another one. Similarly, you go from 3 to 4 and come back, that's another one. So it's giving the same result here. So there are 3 walks of length 2 starting from vertex I and ending at vertex I. Vertex 3, okay? And here, the value is also 3. Right? It's interesting. Similarly, okay, I'll just find out. These are some other results, like its adjacency spectrum. That means it's the spectrum means here the set of all its eigenvalues. Okay, set of all its eigenvalues, including its multiplicity also. Means we can repeat here also. And since all its eigenvalues are real, you can make an ordering, maybe some non-decreasing ordering. And what we have, we can say whether a graph is bipartite or not by just merely observing its spectrum, adjacency spectrum. If the spectrum is symmetric about origin, that means if there is lambda is one eigenvalue in the matrix, then minus lambda should be there with the same multiplicity. Then we say the spectrum is symmetric about origin. If that happens, then the graph, we can say it is bipartite. What is bipartite? Bipartite means you can partition the set of vertices of the graph in two parts such that there won't be any edges between each partition, but whatever edges will be there, it should be from one partition to the other. Okay. Similarly, other properties like if we know this eigenvalue, the second largest adjacency eigenvalue, if it is equal to -1, the graph is complete graph. If it is equal to 0, then it's complete multipartite, and there are many more results. About Laplacian matrices, okay, we have a very good result. It's a very old result known as matrix tree theorem. What it says, it talks about the number of spanning trees and how much it is. The cofactor of any element of L. L is suppose your Laplacian matrix of the graph G. So you are given with a graph, you can form its Laplacian matrix, and you are taking a cofactor of it, and any cofactor, here L11 is coming out 3, any cofactor of it gives you the number of spanning trees of the graph. So here, what are the spanning trees? This is one spanning tree, this is another one, this is another one. There are only 3 spanning trees here, and that is reflected in any cofactor of the Laplacian matrix of the graph. So basically what we are getting here, with the help of matrices, associated matrices of the graph, we are able to tell properties of the graph. Similarly, we have this idea actually in case of Laplacian matrix. Let me show you this. Okay. Laplacian matrix, the way it has been defined, all row sum or column sum is 0. So the vector of all ones is always one eigenvector, and 0 is the corresponding eigenvalue. That's what we say. It's a positive semi-definite matrix, and 0 is always the least eigenvalue, and the corresponding eigenvector is the vector of all ones. Fiedler has proven that the smallest eigenvalue has an important role here. Second smallest eigenvalue. If it is positive, then we know the graph is connected. This is if and only if condition. That means even if it is of millions of points and there are millions of interconnection, the graph may be very difficult to, even by looking at it, it's very difficult to say whether the graph is connected or not. But by knowing its second smallest Laplacian eigenvalue, you can say whether the graph is connected or not. If it is equal to 0, it's disconnected. If it is greater than 0, it's connected. And that's called algebraic connectivity. There are many results related to algebraic connectivity. The corresponding eigenvectors are called Fiedler vectors. There are many results also. Okay. Some further applications, let's discuss. You may have heard about this Buckminster fullerene. Okay, that's from chemistry. What is it? A fullerene is any carbon molecule that forms a sphere or ellipsoid. The connection here is from observation that the sphere of carbon can pretty much only be made when the carbon is joined in cycles of 5 or 6. Actually, carbon means how they are connected. So basically, if we represent them in terms of a graph, that will form actually a 3 regular planar graph, which has phases of 5 or 6 cycles. Okay, so questions like these are generally analyzed. This has been analyzed also. This has been proven also. Many results have been found. What are those questions? What kind of properties do fullerenes have? What kind of graphs can be fullerenes? Means what are those graphs? Which graph theoretic fullerenes? Means we have some graph theoretic fullerenes which is really possible. Okay, so also viable molecules in reality. So these are some questions which are answered here also. And next, I will kind of here by just giving the linear algebra behind Google. So basically, each web page is linked up. Okay, like page 1 is linked to page 2, so it is over this. Then you can see page 2 and page 1 is over 4, and this one, page 3 is not linked to 4 but is linked to 3. So you can basically you can actually I have collected this from this link, and there are some papers or link. You can see this one. this billion eigenvector, the linear algebra behind Google. Actually, the star is for actually during 2004. This was the cost of the result. Okay, the outcome means this gave us the value of this much during 2004. You can imagine how valuable it is. Okay, so what we have done, this we have represented, these web pages we have represented in terms of vertices 1, 2, 3, 4, 4 web pages, and if they are linked, then we have these arrow marks in some graph notation. Okay, so 1 is linked to 3, then 3 is also linked to 1, 1 to 2 there is, 1 to 2 there is, but 2 to 1 it is not, because it is over 2. Sorry, 1 is behind 2, so 1 is linked to 2, but 2 is not linked to 1, right? But here, three and 1, so these are both way. So basically what we are trying to do, I will just tell the gist. You have to go through all these links also and some other papers also. So we form a transition matrix. What we do, if it has one, that means each one is of value 1, and if there are suppose 3 outcomes, then each has to be distributed. That means suppose consider vertex 1, then vertex 1, how many are output from the vertex 1? There are 3 actually edges coming out of vertex 1. So there are from, this is towards 2 and 4 and 3. So the value 1 will be distributed equally. So this comes out 1 by 3 each one. Similarly, from vertex 2, there are only 2 outputs, outward vectors. Okay, so or outward edges. So each will be given half values. And we have constituted the matrix A accordingly, like the adjacency matrix. We call it the transition matrix. And what we try to find out, basically this is a non-negative matrix. All its entries are non-negative numbers, non-negative values. So we can apply this Perron-Frobenius theorem, which says it has a positive eigenvalue, which is of if it is and all this, it has also a positive eigenvalue, which is of multiplicity 1, and the corresponding eigenvector can be considered as all its component as positive. So here we have considered the eigenvector corresponding to this matrix and corresponding to the largest eigenvalue modulus wise. Okay, that eigenvector is this one, and this value, this 0.38, is the importance of this web page 1. This is 1 is more important, and then this one, the next one is 3. Okay, you can see also, you can analyze it actually how it is coming out. Actually, for discussing all this, it requires a lot more time also. We call this as the PageRank vector of our web page. Okay, and to deal with this, to find out what we have to do, we have to first consider a vector, say, which components are 0.25, 0.25, 0.25, means all are of the same value. Then we will start with that. Then we will find out AB. Then that vector will multiply and with the new matrix. That means we'll find out A square V, A cube V, A to the power 4V, and so on. Okay, not that way actually. Okay, if we'll go on doing that, okay, yes. So if we go on doing that, that vector ultimately will converge to this vector, the eigenvector corresponding to the largest modulus wise, largest eigenvalue. Okay, so that's your PageRank. And these are some of the references. This is Slot's paper book. Sorry, this is the book, and there are some books by Buffett also. This is graphs and matrices. This deals with this spectral graph theory also. And this one also another very good book. This is Vedko Spectra of Graphs. And these are some of the other references. And thanks for giving and thanks to the organizer for giving this opportunity to give this lecture.
I answered one question in the drop box, the chat box. Yeah. If he wants to ask furthermore, maybe he can ask directly.
Basically, I have designed this slides so that you will raise a lot of questions from your side, and you can go for smaller examples, and from that intuitively you can get the results. Okay, and you can prove yourself. Okay, thank you.
Excuse me, sir.
Yes.
Sir, when we are talking about the application of singular value decomposition, then when we have talked about the pixels of pictures, then we are talking about with respect to the matrix or its general matrix, sir. As we have talked about the line decreasing the pixels are as the pictures are getting blurred.
Sorry, can you repeat the question? Actually, it was not audible properly.
Okay, sir. Sir, as when we have talked about the application of singular values decomposition, then we are the matrix is decreasing, the pictures are getting blurred. Then at that time we are talking about the some particular matrices, or we are talking about some any general matrices.
No, it's about actually any matrix, no? Because what we are doing, we have actually the singular value decomposition for, which will work for any matrix. So basically, your image is nothing that we have considered it in terms of a matrix, because it's again a pixels. Pixels again actually considers some values, some positive values, 0 to 255, say. So it's 500 cross some value we have got, 500 cross 800 matrix or something. Then